Okay, I think we should start now. It's 9. Okay, good morning, everybody. Welcome to the third day of the summer school. So I'm very happy to have Karl-Henrik with us today. Karl-Henrik is a senior lecturer at the Department of Computer Science and Technology at the University of Cambridge. And he has been working for many years since his PhD on unsupervised learning using Gaussian processes. So very happy to have you as always here, Karl-Henrik, and thanks so much for doing this.
Fantastic. Thank you so much, Maurizio. It is always a pleasure to attend GPSS, and it's really nice to hopefully be able to give this talk. And so what are we going to do today? Well, so I'm going to talk a little bit about unsupervised learning. And then what we're going to see is when I talk about unsupervised learning the way I do it, it's going to be a very, very short presentation. It's going to be about 5 minutes in that case. So what we're going to see is that unsupervised learning, the way we think about it in terms of GPs, very easily leads to composite structures using Gaussian processes. And what we're going to do, we're going to talk a little bit more about them towards the end, and we're going to see some rather challenging and interesting things that appear when we use them. But one of the things that I really like about GPSS is that compared to many other machine learning summer schools, we kind of talk about the same thing over and over again. And I think that's actually quite good, because what it ends up giving you is quite a different perspective on the same things. You have probably seen 2 or 3 introductions to GPs so far, and I'm also going to have my stab at it and give a little bit of an introduction to GPs. But what I'm going to start with is to try and provide a motivation for why I think GPs are really cool and really useful. So to start that off, I'm going to talk about machine learning in general. So let's say this. So if we try and formalize the idea of learning and statistical learning specifically. So let's say we have a space of functions. You can think about this as a space of hypotheses. And then I have a learning algorithm A. So what this learning algorithm does is that it's some form of mechanism that can traverse the space of functions. And then I have a training data set, S. And in this case, we can think of this as, for example, pairs of X and Y's. Most of the stuff you've been talking about so far has been regression. So let's think about what we want to do is we might want to predict Y's given X's. And this sample, this training data set is a sample from the data distribution. So the product space X of Y, there's some underlying distribution over this. And then we need to have some form of measure of goodness. So what we have is we have some form of loss function that basically says something about how well a specific hypothesis or a specific function is describing a specific data point. So what this is here, this object here, is the object that if I take my algorithm A, I take it on a specific hypothesis space, and I take the specific training set S, this here will return one specific function. So how do I actually choose this? Well, a sensible thing would be to take the expected loss over this data distribution. So what you would want to do then is that the notion would be that I would want to be better on average on things that appears often, while I'm okay being bad at things that appear very rarely. So now the trick is, if we could compute this expectation, we wouldn't be here today. There effectively be very little need for machine learning in this scenario, simply because if we had access to the data distribution, there's effectively nothing to learn. We know everything that we need to do. So as we don't have this object, what we often do is that we compute what we call the empirical loss. So what we assume is that we assume that the training data set we have is somehow a representative sample from the underlying data distribution. And we say that every point is equally important, and then we try to minimize this loss. So we try to pick the hypothesis that would somehow minimize this thing. Well, the tricky thing about this is that, in effect, I can give you a combination of S, A, and F, so a sample set, an algorithm, and a hypothesis space that makes this error take a completely arbitrary value. So to make that a bit more precise, let's start off like this. So we have this plane, and now we're going to start seeing some data. So if I see one data point here, there's infinitely many functions that passes through this that will give me a completely arbitrary error anywhere. When I see more data points, I see a second point. Now I'm removing lots of possible functions, but there's still infinitely many functions that passes through this. You can keep doing this. And of course, every time you reduce the space of, you reduce the possible solutions, but even if you see infinitely many data points, there's still infinitely many points that will, infinitely many hypotheses that will go through this. So I like to draw this Pareto front, or this image to show what I'm trying to say here. So on the x-axis here, we got data, or the volume of data that I have. And on the y-axis, I have the set of assumptions, or the set of knowledge that I input into a system. So on this line here, so what this front encodes is a scenario, a combination of data and assumptions that allows me to solve a specific problem. So on this point here, all the way out here, I'm in a scenario where I've seen everything that I'm ever going to see. And in this case, data is the only thing I need. Basically, I don't need to do learning at all, because effectively everything's just a lookup table. On this point out here, I have seen nothing, but I got perfect knowledge. And if I got perfect knowledge, there's nothing I need to learn either. I already know everything. Machine learning is the thing that sits somewhere in here. And what mostly we're interested in doing is to exploit as much knowledge as we humanly can. And we like to come up with models or methods that allows us to input the knowledge that we have in as many ways as possible, so that we can move up this axis, so that we can reduce the amount of data that we need. So then this one, we hopefully get the x-axis, but what is then the y-axis? What does it actually mean to have an assumption, and what does it mean to parameterize knowledge? Well, now if we go back to the scenario that we had before with these three components, the A, the F, and the S that we talked about in terms of the learning system. So what you can do is you can input knowledge into the algorithm, so the thing that traverses the space of functions. So what you can say is that you can try and find between these solutions that would all be potentially giving the same error, you can now say, actually, I'm going to make sure that my algorithms do not walk left, because I really want that solution to the right. That would be like putting a patch over one eye. You might have that this solution here that gives a very small error, it's just a very narrow range of parameters that gives me exactly that solution. So I'm going to put on really, really large clown shoes to make sure that I don't step into that hole. So this will become a little bit like what I like to think of as Monty Python's Ministry of Silly Walks, But this is a sensible way, or it is a way to include knowledge to somehow regulate the problem so that we can find a solution. And this is often what happens in models such as neural networks, where most of the regularization, how we can actually find a solution, comes from constraining the algorithm that searches for the solution. The other thing is that we can alter our data space. We can, for example, arbitrarily expand our training data set. So this is often done, say that we have images and we want to include something such as a rotational invariant. What we can do is we can take our data set, we can rotate all the images, and we can include them as well. This is, of course, very, very expensive often to do, because what we really were out for is to reduce our use of data. And in this case, we're effectively expanding it. And the last thing, which is what really we are doing here this week, is to think about how can I directly include knowledge into my hypothesis space. So how can I reduce the set of possible hypotheses, or in place some form of structure on the space that I'm searching over? So this feels really hard because it kind of becomes a chicken and an egg problem. If you know what you're looking for, why do you actually need to go out and look for it, right? So now what I effectively explained through this statistical learning scenario was the no free lunch theorem. And if we talk about the hypothesis space specifically, there's this notion which I find really, really annoying in machine learning, and it's the use of the word flexible. There seems to be this narrative that what we're actually looking for, a good model or a good hypothesis space, is something which is very flexible. And the more flexible it is, the better it seems to be. So completely the opposite is true, right? So what we actually want, what we really should be happy about, is we find an incredibly inflexible model. We want something, potentially, an ideal model, should be something that has infinite support. So what it means is that nothing is excluded, but it has a very, very focused mass. So it's something that I can input very, very strong assumptions in. Because if I do that, then I can use very small amounts of data. But obviously, the things that I include needs to somehow be relevant. And that's the really tricky thing. So the next thing, what you want from the assumptions that you put in, is that they should somehow be interpretable. Because, and the interesting thing about this is that if your assumptions is not interpretable, you can never ever interpret your results either. Because the only way you can say something about the solution that you get out is that you say, I think this, now I test this based on data, and that somehow justifies what you started off with, what your prior assumption is. So this, to me, is really what GPSS have been about, right? So you've seen this really a lot, hopefully already, impressive results on Gaussian processes learning quite interesting things from very, very small amounts of data. And what that effectively means is that a Gaussian process specifies a very, very strong prior, which means that it's in effect a very, very inflexible model. And that's exactly what we want. Cool. So now I'm going to do my reasonably short introduction to Gaussian processes. You've seen this done quite mathematically, so I'm going to do a much more intuitive or try and provide a bit more intuitive introduction to GPs. So we started off and said that the thing that we really want to do is to specify some form of structure over a hypothesis space that is some form of functions. Okay, so now we have this plane, and it feels kind of hard. How would you parameterize something, as we said, that ideally includes everything. Everything should be possible, but it provides the possibility of really narrowing down and saying that there's very few things that are very likely. And how do we do that without excluding too much? Well, let's do this. So let's draw a slice at x equals to 3. One thing that we know about the function, any function, is that it would have to cut this slice once and only once. So what we can do is that we can parameterize the function itself through that intersection. So what we're going to do is that we're going to parameterize that intersection as a Gaussian. Okay, so the nice thing now is that we've now said that any intersection is possible. The Gaussian has mass up to plus infinity to minus infinity, but we can shrink this mass so that it's very peaked around a specific location. So now that includes every possible function parameterized at x equals to 3. So now there's nothing special about x equals to 3. We still haven't seen any data. So if I make this argument that x equals to 3, I can also make this argument at x minus 2. And I can then do quite a lot of slices. I can do very many slices. I can actually do infinitely many slices. So now, if I take this Gaussian and I basically do infinitely many slices of this, now we have a Gaussian process prior. So far, this isn't a particularly interesting parameterization of a function because it only talks about the intersection at one slice. And the interesting functions are functions such that two slices somehow depend on each other. The knowledge that I have about one slice says something about the intersection on another slice. So if we then take two of these, so we go back and we take minus 2 and we take 3. So let's say now that we know the intersection at minus 2. Or actually, we know it very well, but we're a little bit uncertain of it, right? So we now have this very peaked Gaussian at minus 2. We think the intersection is at 2. So now the question, the parameterization that we want to have is that what does this knowledge tell us about the slice at x equals to 3? Well, one way is to say that it tells us nothing. So then we're back to where we started, our prior assumption, before we knew anything. So that says that minus 2 tells me nothing about 3. Or the other extreme is that it tells me everything. So knowing the slice at minus 2 provides me with perfect knowledge at the slice at 3. Or most likely, it's somewhere in between. So what this then is, it's the covariance between minus 2 and 3. So this now, we can parameterize these two slices, and you've seen this, we can parameterize as a joint Gaussian distribution. So the value at x equals to 1, the y value, how that co-varies with the y value at the other slice. And this covariance object then specifies exactly how much information flows between these two slices. And the trick with the Gaussian process is that we parameterize this object here, this covariance element, by the location, by only the value at the input. Cool. So now, as we started off, we said, well, you can take infinitely many slices. So if I now take lots of these slices, they only define a very high dimensional Gaussian distribution. I can draw a sample from that, ta-da, and we see these nice things. So now, to highlight a thing, When you first look at this, the first time I saw this, I thought, wow, this is so cool. Look at this. This represents so many different functions. And it doesn't, right? Because actually, and this is the really interesting thing. So all these functions look actually very, very similar. So the difference is the parameterization that we have in this case. By parameterizing a function, its term of its output, in this representation, these functions are incredibly similar. So the next thing that is very cool with this, and you've also seen this, is that what we can do is that we can do posterior inference in closed form. So if I now have my prior that I've drawn these samples from, what I want to do is that I want to see some data, and I want to now see only the functions that are consistent with this observation. So the normal way you would do this is you would write a for loop that would go from I equals to 0 to infinity, and it would then have an if statement that checks, does that function pass through this point? If so, then it has non-zero probability, otherwise it's at probability 0. Now, that if for loop with an if statement would be very expensive to compute. The really cool thing is you guys did that with a tiny bit of linear algebra, and you directly get this distribution. And that is very, very cool. So the last bit that I just wanted to say, I found, having done GPs for many years and having taught this many times, I found the biggest challenge to understand GPs is to get over the fact of how incredibly mathematically simple these things are. They do very cool things, and you kind of think, therefore, they have to be complicated, but they aren't. They're actually really, really trivial. And the best way, I think, is to learn them is by actually deriving these 3 Gaussian identities. So actually going up and seeing, actually deriving by yourself what the marginal and the conditional distribution is from a joint Gaussian. And I think this is something that's really worthwhile to do once. Cool. So that was basically my introduction to GPs. And now we're going to move on to the meat of this talk. So we're going to talk about how we can use these things for unsupervised learning. So unsupervised learning is not particularly different to the supervised learning that you talked about before. So we've seen in supervised learning, what you've seen is that you have some data, some output data Y, and you have some input locations X associated with them. And what you're trying to do, what we're always trying to do in machine learning, is that we're trying to learn a distribution over our output data. So we're trying to parameterize P of Y. But in supervised learning, we're trying to parameterize P of Y using X. So effectively, we're trying to, now this is sloppy statistics, but in machine learning, we would say that we're trying to directly parameterize the conditional distribution P of Y given X, so that we can do predictions, we put in X, and then we get the distribution, a conditional distribution over Y. So in the unsupervised scenario, we do not observe X, so we do not know X. So what we're trying to do now is we're trying to only describe this distribution over Y, still parameterized by X, but we need to find the X's ourselves. So if we draw that graphically, it looks a little bit like this. So think of an abacus frame. So you've got X and you've got Y. We've only been given Y values. So we've got all these stars, which are our Y values, but they have no corresponding X. And our objective is to give each of these X values or Y values an X value. So we want to somehow pull these stars along and give them an X location. So some examples of that would be this. Here I've given these y values some x values, and I've connected them up. This here is another one, and so forth. Here's a third one. So there's again infinitely many combinations of doing this. So how do I somehow regularize my solution space so I get something sensible, something that I want out from this? Well, we're going to use GPs to do that. And the way we're going to use GPs is that you can see from these combinations here, this is one function, this is another function, and this here is a third one. We're going to use a GP to specify a preference over which of these functions that we like. And if we pick a function that we like, then if I know f, I can from there get x. And therefore, that is doing unsupervised learning. So in this case, here, I've taken a GP prior. I'm always going to use the same prior. And then I given each of these y values an x, and then I put this GP through this. Now I can evaluate how probable this function is compared to, for example, this one, compared to this one. And then we're effectively going to pick a distribution that is more of functions that is more probable under that GP prior. So we're using the function itself to constrain this. Right. So let's then say that what we've done is that we like solutions that are smoother than not. That's how we've parameterized our GP prior. We have a preference towards smooth functions, so things that are very, very quickly varying, we like less. But there's a get out of jail card here. So let's say that you're completely free to choose the x values to make the smoothest possible function. Well, there's a very easy way to do that, is you can push the x values really, really far away from each other. So now you can effectively make a line out of anything, right? You can make something really, really smooth. So that's not good, right? So what we need to do is that we need to add an additional prior as well. We need to somehow add a constraint on x. So, or a preference over x. And this is something that we often find in any type of Bayesian modeling, where we have a parameterization where we need to place multiple types of priors to balance out the problem. So in this case, what we need to do is that we need to place a prior both over the function, so how the x and y's are structured together, but also we need to place a preference over x, right? So P of f given x, so our GP prior, this is what you've seen so far this week. It describes our belief or assumptions in what we think the function, the structure is. And another way of thinking about it, it defines our notion of complexity in the function. And P of x then expresses our beliefs and assumptions about the structure of x itself, or our notion of what we think is complex in this space. Fine. So now we can just churn the handle. So let's say that we specify some prior over x. We have our GP prior. Now we just need to compute this, right? So let's go back and think of how this actually looks like. So we've got our GP prior, some Gaussian structure looking like this. So you've seen this, it's an exponential, and inside the exponential, in an inverse, we have the covariance matrix. The covariance matrix itself is where x comes in. Let's say now we have a covariance function, which is some form of exponential. That means that each element in this matrix inverse is some form of exponential function. And inside that exponential sits x. Then we have a likelihood function, and these f's here, which then comes from these x's, sits also in an exponential. So now let's just think if we want to integrate these x's out. So these x's goes specified, we have this distribution over x that should then go through this exponential, and in this exponential, it sits inside this. This is going to be really, really tricky, and it's in fact something that you cannot compute. This is analytically intractable in most cases, so we simply can't do it. So I think Neil's giving a talk after me this afternoon. He most likely will mention Simon Laplace. I'm just going to have one quote from Laplace today. Apparently, he said, nature laughs at the difficulties of integration. So this is the case. We cannot compute this tractably. So what we need to do is that we need to do some form of approximation. So the next bit of this talk is going to be about how we can approximate this integral to do unsupervised learning. Now, I know you've seen, especially T's talk yesterday, there was quite a bit of approximate inference. Some of the things that I'm saying, she's already said. I'm saying it in a slightly different way, and I hope it will be useful to have seen this twice. So we're going to simplify things a little bit to begin with, and we're not going to talk about GPs. We're going to do this for the very general case. So what we have, which is pretty much anything that is machine learning, is that we want to find some distribution P of y. We cannot directly parameterize P of y because we don't have knowledge of this directly. What we have knowledge about is some variable x, and we can also formulate dependency between x and y. And now we want to integrate that out. We want to average out our knowledge to get this distribution P of y. And in this case, this integral itself is intractable. So what we're going to do is that we're going to follow Laplace, who says that the integral, like nature laughs at the difficulties of integration, so we want to avoid integration. So this here, so the leftmost model, is what we've defined. This here is our statistical model that we've written up. What we want to reach is this thing, the distribution over y when we integrate out everything that comes from x. We can't compute this integral. Annoying. But then there's another thing that we cannot get because we don't have this. And that is, if we write P of y, there's another way of writing P of y, and that's writing base rule in a slightly weird way. So base rule, we can think of as I have my likelihood times my prior divided by my posterior is also this distribution. So now, because I can't compute this one, can't really get this one either. But what we're going to look at is that we're going to think maybe it's easier to find this distribution. If we can find the posterior distribution, effectively we can use base rule to get this one, right? So what we're going to do is we're going to do variational base. So what we're going to try to look at is that we are going to formulate a new distribution, what we call a variational distribution, Q over X, which is parameterized by some variable theta, which we're going to call a variational parameter. And then what we hope is that we're going to try and learn theta such that theta contains all the information about X that comes from Y. So we can effectively cut this dependency. And then if we manage to do that, that means we got an approximation of the posterior distribution. And if we have an approximation of the posterior distribution, well, happy, joy, joy. Then we also, through Bayes' rule, have an approximation of the marginal likelihood, or the evidence term here, the thing that we were actually looking for. So what I'm going to do is that I'm first going to go through how we do variational Bayes in general, and then from that I'm going to go through the special formulation that we need to use to do this for Gaussian processes, because it doesn't work directly out of the box. So the object that we were looking for was P of y. What we're going to do is that we are going to look at the log of this distribution. The reason why we're doing this is because we're later going to derive a bound, and we need a function that induces this bound. We're going to use an inequality. The other way of thinking about why we're always doing the log is that most things here, most of these distributions that we're going to work with are somehow going to be exponentials. So it's always much nicer to work in log space. So what I'm going to do is that I somehow want to connect the evidence, so P of y, with the posterior. So I'm just going to write this silly thing. This doesn't mean anything, right? So I effectively got just adding 0, but now added the posterior. And then I want to write these two terms both on integral form so that I can merge them and connect them. So I'm going to add an integral over this part here, q of x dx. And q of x here is my variational distribution. And q of x is just any distribution. So if I integrate that over x, it just sums to 1. And I just get log p of y in this case. And here, nothing happens either. So then what I can do is I can merge these and put them on the same form. And now what I have is that I got q of x log, and then up here I got the posterior times the evidence, or the marginal likelihood, divided by the posterior. So now the nominator in this case is just the joint distribution. So now I have the joint distribution over the posterior integrated over this q of x. So what we're going to do now is that we're going to split this log. So if I now split this log, hopefully this doesn't go too quickly, I put q of x log, and I have the joint. Remember here, the joint is something that I can get, because if I formulated my likelihood and my prior, this is just a multiplication. So hopefully this is something that I should be able to get. And then I'm going to write this q term here. This means effectively nothing. The reason why I'm writing this is that I want to spread out one of these q terms. You're going to see that a bit later on. So if I move effectively this q term over to this end, now we have this expression. So what is this expression? Well, I have something on this side, the blue terms. This should be something that I'm able to potentially compute. At least I have all these terms. I've got the joint distribution, which I can formulate, and then I got the expectation over q of x. Then on this side, I got something which is just in terms of q. If I'm allowed to choose q myself, I should hopefully be able to compute this. The bad side is this part here, because here I got the posterior distribution, which is something that I do not have, right? So if we then look at that red term, we are going to have to now formulate a bound. And this is what we're going to aim to formulate. So we're going to exploit something called a Jensen's inequality. And this is very simple. So if I have here the log, if I take and move the log outside the integral, this is going to be an upper bound on having the log inside the integral. So if I do that, so we're going to use this on this. So we look at qx log q of x divided by the posterior. So I'm just flipping the log, changing the sign, and then I apply this Jensen inequality, so I remove the q terms. In this case, I'm just integrating the posterior over x, which is just 1, so this is 0. So I know that this term here, the red term, is lower bounded by 0. And then something even more simple, if I now pick q of x to be the posterior, obviously now this term inside the log just becomes 1, and in this case it's 0. So I have now a term, this red term, that I know is 0 if q of x is equal to the posterior, and in all other cases it's positive. So this term then is what we call the Kullback-Leibler divergence. So you can think of this as a measure of divergence between distributions. It's not a metric, but it's a notion of divergence. So what we can then do is that I have these two blue terms that I hopefully should be able to compute, and I have this red term which I can't formulate. Now, as I know this will be positive, then I know that this blue terms is then a lower bound on the log evidence. And this is then what we call the evidence lower bound. So this was a very confusing, potentially, derivation of variational base. So very often when people define variational base, they start off with the KL divergence and they say, great, the KL divergence is some form of measure of similarity. And what I'm going to do is that I'm going to try and minimize this measure. I think this is a bit of a strange way of deriving variational base. And the reason why I did it in this way is what I wanted to say, what I really wanted to show is that we're trying to find P of y. So we're writing up this thing here, and then we're exploiting that this thing here is positive, and this leads to the bound. That this here is the KL divergence comes because we're exploiting the log to induce this. We're exploiting the log as a function to get this lower bound. And using the log is why the KL divergence pops up. But you can do this in many different ways, as long as you're using some form of function that allows you to induce an inequality. So what we've effectively done is that we've now formulated the marginal log likelihood in terms of two terms, a KL term and this other term that we should hopefully be able to compute. So what we can do, what we're going to try to do is try to maximize this term, because if we're maximizing this term, we're minimizing this term, and we know that it's minima. This thing here is 0 if Q is equal to P. And then we have achieved that the Q distribution actually is our posterior. And that is variational base. So we try to find Q of X to match our posterior. Right. So let me just jump here. So now let's try to do this with a Gaussian process. So what we do is we formulate this term here. So this is just taking exactly this bound here, but I've moved the Q in here to write it just as one expectation. So we have this here, and this is now what we want to describe. So what we do is that the joint distribution we now can write up as our likelihood term, our Gaussian process prior, and the prior that we had over the latent space. And then, oops, sorry, we can now move out this Q term that we had here. And what this term here is that it's used basically the approximate posterior in relationship to the prior. And then we got this term here, which is our GP prior, our likelihood, and then we got Q. So now, this term, to just make the math a little bit easier or a little bit shorter for me to write, I'm going to remove this term and focus on this one. This term here we should be able to compute. So if we look at that, have we actually alleviated any of the problems? We haven't. So now we're still basically in the same situation as before. In order to integrate this, we still need to push this X through a nonlinear mapping for it to reach the data Y. So this thing here is still untractable. We haven't actually done anything. So doing variational base on a GP is not just straightforward. So what we need to do, so the way you move forward, is that we do something which is called a sparse approximation. So we're going to use something called inducing points to do this. So what we're going to do and how this is based on is that we're going to say this. We are going to take our GP prior, but write it in this form instead. So what this is that we got some slices, F. I'm now going to add an additional set of slices U. The slices F are at the location X, and the slices U are at some location Z. Now, this GP prior, I can now write as this. So this is just manipulation of Gaussians. So I can write this as I first take the slices at Z, the output of those are U's, and then I write the slices of F conditioned on these U's. So this is just very simple manipulation of Gaussians. So if I write that up as a conditional, as how that Gaussian will look like. This is exactly the predictive distribution of a Gaussian process that you've seen before. So basically, when I predict the locations of F, I use the outputs I had at U prior to that. So importantly, we've done nothing to the model. The only thing we're doing, the only difference that we've done is that we had some slices or some marginals F that we were interested in. Now I've just hallucinated, I've pulled down a few more slices at some locations Z with some output U. The difference now is that we're going to take the same non-parametric view as we took when we specified the GP prior of these U's. So we are now going to think of these U's and sets not as random variables from this GP. We're going to look at them as variational parameters. We're going to use these U's and Z's to parameterize the variational distribution Q. So remember that variational distributions are approximations to intractable posteriors. The way we do it is that we have this sketch where we had a Y, an X, and we added a theta in, and we said this theta now contains all the information about X that was contained in Y. That means I can cut the dependency between Y and X. So Q of U should approximate the distribution P of U given Y, X, Z, and F. Q of F should approximate the distribution P of F given U, X, Z, and Y, and so forth. So this is what these variational distributions should do. And now, what we are going to do is that we are going to use these as I said, as variational parameters. So exactly like those thetas were. So that means that if these u's contains all the information that existed in y, that means we can cut the dependency of y. So that means if this is true, so Q of f is supposed to approximate this distribution. That means, if this is true, that we can cut the dependency of y. We can cut that edge. So let's see what that actually means. So in this case, now I put in all the distributions I have, all these approximate posteriors. I got Q of f, Q of u, Q of x. And then up here, I have my, one of these should be u. Sorry about that. And remember, x should have been on this side, but now previously, we picked out the p of x so that we got x on the right-hand side of conditioning. So now we are going to use, now in this case, we have written out, and hang on. Yeah, now this one's written the right way. Skip this one, it's confusing. So now what we do is that we take this joint distribution and we write it up as the likelihood, the GP prior that we had, and then this GP prior over u. So we write that as this conditioning. So we first pick the u, and then through u, we predict the f's. So then we go back, and now the question is, how do we pick these distributions, the posterior? Well, from the argument that we had before, we're going to assume that these random variables, or these variational parameters u, are sufficient statistics for f. So that means we can cut the dependency between f and y. So that means Q of f will be this. So now if we put that in and we start writing this up. So this is just exactly the same thing as we had on the previous slide. And then we now introduce the Q of f as P of f given u x z, right? So this should normally have a y in it, but we say that u encodes all the statistical information about f that y contains. So now something interesting has happened. So you see that this term here, which comes from how we wrote down the joint distribution, is the same as this. So what we can now do is we can cancel these with each other. So if we cancel these with each other, we end up with this expression here. And now this expression is very, very different, because what we've effectively done now is we've disconnected x, right? We now have the u's, and then we have the f's here. We've disconnected that path where it had to move through this nonlinearity. And because of this, this is actually something that's tractable for us to compute. So if we do some manipulation of this again, what we end up with is that we need to take the expectation over this likelihood term over this GP prior, and then we have a KL term again between the posterior over u and then here the prior over u. So what does this lead to? Well, now we actually have a bound, and hopefully we should be able to compute this. This here is the tricky term. The expectation here is the tricky term to compute. You can do this in closed form for some covariance functions, and others you can't. But what you can actually do in many cases is you can actually sample this thing itself. Another thing that this has allowed us to do is you can do stochastical inference over this. And there's this paper here by James Hensman et al. That shows how you can, in this case, use batch inference, and that means that you can use much, much larger data sets. But for us, the interesting thing which we need to the next part of the talk is that the term P of X, remember that's how we started with the unsupervised learning. We wanted to have this description, this notion of complexity, this assumptions over the latent space, and we wanted that to filter through all the way to the data. In this bound, P of X only appears in this KL term. And this is really, really nice, because that means we have a lot of flexibility of introducing priors over the latent space, because effectively it's only this KL term. As long as we can compute the KL between the distribution that we pick, the Q of X, and this distribution, our prior distribution, then we're fine. So what can you do? Well, some ideas about latent space priors is first this. So we started off by saying there was a get out of free jail card where the latent space could just become the X locations can become super distant from each other and therefore create a very, very smooth function. But what you can do to penalize that is you can put something as simple as a Gaussian. So if you put a Gaussian, that would prefer to push the latent space together. And now when we do inference, there's going to be this really nice trade-off between two things. So the function wants to, for example, put smooth functions. Well, it also has to trade that off with that it has to be smooth, but the X locations can't be too far away from each other. So there's a balance between these two. Another thing that you can do is you can do what we call automatic relevance determination priors. And what this means is that you include a scalar variable for each dimension on the latent space. And then you place this Gaussian prior over the latent space. And now this scalar parameter effectively allows you, if this goes to 0, that dimension is gone. You do not use it. And because that Gaussian, the latent Gaussian, is effectively now, it has the possibility to make things more likely by reducing the volume of the space. So now you get this trade-off where it says the ideal scenario is that, well, I'm not going to have any latent dimensions at all. Well, then you can't represent the data. So now you get this nice trade-off with having few latent dimensions and representing the data well. And with this, you can learn the number of latent dimensions that you want. Another thing is you can do things like dynamic space, the dynamic priors. So you can have a latent space where you say, well, my data is somehow sequential. And because it's sequential, I can have a prior that says I'll start off. The next point in a sequence should actually be close to the previous point in the sequence. So you can do this autoregressive prior, and from that, you can parameterize things like motion capture, for example. This is often done by placing a GP, an autoregressive GP, over the latent space itself. And then we got the next thing, which hopefully will lead me to the last bit of the talk, and that is, well, we started off here and said, cool, let's place a distribution over X itself, try to integrate that out. We managed to do that approximately, and the way the X appeared was that just this simple KL divergence. So that leaves us basically with having pretty much any distribution over the latent space itself. Well, how about we say that that distribution comes from a GP itself? So what we now have is that we have a GP prior over the latent space that then goes through a GP to generate the data. Well, if we do that in one step, what we can do is we can just say, let's have a GP prior over a GP prior over a GP prior, adding phenome. So what we've effectively generated in that case is what's called a composite Gaussian process, or as some people like to call it, a deep Gaussian process, where we've just said we can write a GP in a GP in a GP in a GP, and so forth. And we can do that exactly in the same way as we did the unsupervised learning. It's exactly the same type of bound, because we have effectively disconnected through our bound, through our approximation, the latent space prior going through. So now we can simply add GPs together in this way. Cool. So now, Maurizio, how am I on time?
You're great. You have half an hour more.
Oh, I have half an hour more. Very good. So basically, what I wanted then was to spin on this a little bit more and talk specifically about these composite model structures. So this part is going to be a little bit more hand-wavy, and I'm going to try and provide a little bit of intuition about what these models actually do. It's going to be much less math than we had in the previous part.
Hi, we've got a quick question as well from Simon.
Shoot.
Okay, to interrupt. Okay, cool. He says, from my understanding, or for my understanding, do we recover the standard GP approach if the induced latent points are rather observed than latent?
So hang on, can you repeat that?
Yeah, I don't know whether this question quite makes anyway, I can read, I'll just read the words and then you can interpret. Do we recover the standard GP approach if the induced latent points are rather observed than latent?
Yeah, absolutely. Yeah. So I think what we're effectively doing with the inducing points is that we're just adding a set of hallucinated locations. So you can think about it like this, right? So I'll try and get to the answer to the question. So you have this function that goes like this, and maybe you've observed points here on these. You've observed 100 equidistant points. Now you say, I'm going to have 5 inducing points, and then you optimize the location for these points to fit the bound. What is then happening is that you're basically finding a couple of key points, 5 key points somewhere that can really nicely represent this function. So now your question is, if the inducing points were observed, does that just reduce to the normal GP? Yeah, absolutely. If they are now observed, well, it's just the same thing as we had before. Now you've observed 105 points on a function at the end. And actually, so a story is that before this variational bound was formulated, we used sparse GPs in the set that to get them to just compute speed-wise. We said that, oh, you gave me 400 data points, or 4,000. When I did my PhD, 4,000 was like infinitely many data points. So I couldn't compute that. So what we did then is that you took a subset of those data points for training, and then you predicted the rest through them. And that is effectively what you're saying. It was just a standard GP. It's just that I only trained, that I parameterized them using just a subset. So hopefully, does that answer the question-ish?
Yeah, feel free, Simon, to post another question if it's not clear, or we could even unmute people to ask questions if they're still stuck. An anonymous person asked, "What are some choices of Q in this case?"
Yeah. So the normal Q, right? So if you do, for example, if you have no idea of what kind of latent space you want, but the only thing you want to do is say limit you want each dimension to be roughly having the same variance, and you want them to be of ish the same scale, then, you know, a Gaussian blob like this is very sensible. Effectively, this becomes PCA, right? If you pick a linear kernel, this is PCA, because PCA is based on having a linear prior or a Gaussian prior over the latent space like this. Then, you know, a dynamic prior such as this is also another thing that one can do. There's a lot of possible work on this that we can think more of that hasn't been explored. So there's a lot of work and a lot of possibilities to put this on simply because of this. It's so easy because it has this disconnected term. It just sits out here, which is very, very nice. Cool. I'll continue, but please come up with questions more. I know it's a bit tricky. Yeah, shoot.
Yeah, sure. From Nicole. Can you unmute me, Nicole, if you want to ask it directly?
Yeah, sure. I was asking if you can provide, please, some real-world examples from analysis and from data that the composite models that you refer to are more suitable than simple GPs?
Oh, we're going to come to that. This is the perfect question when you feel like that's the next slide, because that's what's coming on the other side of these slides. I'm going to give you some examples of this.
Okay, thank you.
Cool, thanks. Cool, yeah, go ahead then. That's all.
Yeah, so go ahead. That was perfect, Nicole. So let's move on to this. So basically, when you look at this, there's something that should start appearing, right? This looks like something that you might have thought about before. And that is that basically when we look at these kind of model structures, there is this pink elephant in the room, right? So you've through this week heard people basically talk about reasonably dull things. They've been reasonably, before me at least, reasonably mathematically precise, talking about statistics and motivating how we should do certain things to learn from data. You haven't really heard anyone who said, my work is inspired by the brain, or all this nonsense that a substantial part of the machine learning community talks about. But this kind of model structure starts looking an awful lot like a neural network, right? So have we, after all this work, ended up in that very boring place? Well, what I thought I should do is, because we kind of need to talk about this, we should talk about the connection between neural networks and Gaussian processes, because it's something that I find has been, there's been two such separate communities, and that's never a good thing. So what is a composite function? Both of these things, a neural network and a composite Gaussian process, the only thing it is a function in a function in a function in a function. So what is the benefit of doing that? Well, let's just think what a composite function is to begin with, right? So here I have three functions that are put in a composition. So I have my input location 2. I push it through the first function, I get 7.5, put 7.5, I get something close to 1, something close to 1 gives me something 1.2 or something. So that means that if I plot this as a function itself, the composite function, I get this structure. And this is kind of the benefit of writing compositional functions, is that this behavior here is actually quite a challenging function to write, because this has a lot of different types of behaviors. It has this periodic type of behavior, but then it also has this behavior that the length scale, if you want, kind of shrinks. It goes quicker and quicker the further we go in X. And it also has this thing how it's very, very bounded in Y. It goes between 1 to 1.25. And the idea of compositions is that I can specify a wide range of different behaviors by taking a simple set of functions, and then I can put them together in lots of different ways to get these different types of behaviors. That's the notion, right? And it's the programmer's dream, right? Because then it's all, I can just write this perfectly, this perfectly, this perfectly, and I get lots of variability by just connecting them up in different ways. So then let's think about what is it the compositional functions actually do more than this. Well, to begin with, we need to have two characteristics of the function. So the first thing is we have the image of a function. So that's the number of possible output values a function can take. And then we have the kernel, which is all the values that maps to the same value. So all the input values that maps to the same output value. And the two things that we know for compositional functions is that the kernel, the more compositions that we build, the kernel is going to grow. The set of possible points that maps to the same is just going to get bigger and bigger. And the image is therefore going to shrink. So the possible output values to have is just going to get smaller and smaller. So the easy way to think about this is that just take this function here. If I would take these output values and push them through a next function, this point here and this point here maps to the same y value. And therefore, when I push that y value through the next function, well, there's only one, right? So another way of thinking about this, I take a piece of string, each layer takes 2 bits of the string, ties a knot. That knot can never ever be untied when you go through. Okay, why is this beneficial at all? Well, in a neural network setting, say if you're doing classification, it's super beneficial. So I have a very large database of images of my mum, and I would like to classify them all as my mum. What am I doing? Well, I'm taking a very large set of points, and I just want to map them to one. That's effectively taking the image space and tying a knot of everything that is my mum. And eventually, boom, I can just associate the label to that. Another thing, if we now go back to thinking about statistical models, why would you ever want to do this? Well, if your prior knowledge is composite. So remember where I started off, I said what we really want to do from a good model is that we want to specify what I call handles, such that the knowledge that we have, we can input that into the system. Because if we can input it, we can constrain the solution space as much as possible. Here's an interesting paper that actually uses Gaussian processes. And this is to model wind farms. So what happens in a wind farm is that we've got some wind blowing. It comes from one edge. Then it goes through one of these turbines. It generates electricity. What happens at this turbine affects the turbine behind. These turbines we've built ourselves. So we actually know a lot about them. So if I decompose this system into wind coming in, going through turbine, I can now use the knowledge I have of the turbine. If instead I would just say input is wind, output is electricity, the sum of all these, I can't use that knowledge. And therefore, I really want to have a composite function. The other thing that I think about is if I have, say, this transformation. So I want to go from the blue square to the red square. And what I want to do that is that I want to decompose this into a set of simple transformations. I just don't want to learn one function. I want to say, no, this is a composition of 2 transformations and 1 rotation. And I want to write it like this. This would also be a compositional structure. And that is something that I often want to do. And then my last bit is just that if you do GPs, you basically also want to hang out with the cool kids, right? So you really want to build these composite models because it's just kind of fancy, right? Well, jokes aside. So the next thing, so early, very early, so it's mentioned among other things in Bradford Neal's book, but people have known about this quite a long time, is that if you make a neural network infinitely wide, then it effectively is a Gaussian process. So now that is not very interesting. Well, potentially. What is interesting is that when you train a Gaussian process, you can say that you're training an infinitely wide neural network. But the operational regime is not that you use infinitely wide neural networks. You couldn't parameterize them. So the more interesting thing is to actually look at the finite setting. And what we can look at instead is to look at the predictive distribution. So that's actually the interesting thing, right? So the distribution that we do once we have a trained model to do predictions. So the way we formulated, remember, the approximate posterior that we did before, Q of F. This is the thing that we do predictions from. It looks something like this. It's a Gaussian process. It's the normal predictive distribution that you have, where you say, to predict F somewhere, I have these inducing points, and then I just predict. So now, to compare a neural network and a Gaussian process, the neural network doesn't have uncertainty to it. So we're actually only interested in looking at the mean. That's the thing that we can actually compare. So if we then look at the mean, the expected function value, it's just this. And actually, if you look at this, this is only a linear mapping. It's a completely linear mapping. And the only place where the x comes in is in this part here, which is the covariance between the points where you're interested in and these inducing locations. So another way of writing this is just as this linear mapping here. So I have evaluate, I take my input point, I evaluate that, the covariance with these inducing points that I've learned, and then I have a linear mapping of that. So now, if we write this, we write out both the GP prediction and the Gaussian process prediction. You're going to see something quite interesting. So you saw the last talk yesterday, I think, was on multi-output GPs. The prediction I wrote there before was not from a multi-output GP. There's only a slight difference in this case. But if you would write a composite GP, the interesting one would be if you have a multi-output GP at this stage. And if you now want to push this mean through each layer, it would basically just look like this. So in the first case, there's be a C here. You effectively have lots of these linear mappings just pushing through each other, where the nonlinearity is the kernel function evaluated with the inducing points and the data points. And then now if you compare that with a forward passive neural network, it looks basically exactly the same. You have your input location, you do some linear mapping of that, you have a non-linearity, then you have a linear mapping of the output, and it goes forward, forward, forward. So effectively, if you want to write down an equivalence between a composite Gaussian process and a neural network, the only thing that you have to do is write down an equivalence between this activation function here and this covariance function there. So they are different in many ways, because if you think about how the covariances we've defined actually looks like, what it does is that they have this inducing location, and then we have this local dependency. Often we define these squared exponential functions, which says that the closer you are in x, the more they covary. And then the further you go away, they covary less. So the GP often defines these types of basis functions where there's a local influence over the x-axis, while the neural network specifies these global dependency structures. So these magenta curves here, which basically says something completely different. However, it turns out, and this is quite a recent paper by Vincent Portordi, who now shows what you can define these equivalence classes. And if you define this equivalence class, you can write down, for example, what is the covariance function that would lead to a ReLU network. And this is a very recent paper, but it's really interesting. You also has, you've seen part of this, the basis that this works on, I think, from Nicolas' talk on the first day. So this is really cool. So what we now then have is that we have this equivalence class. Well, we know it is possible. I don't want to really dwell into the exact how this is done, but if you believe me, that there is this way of effectively writing down a neural network as a GP and a GP as a neural network. So then what that leads to is like, okay, so if these are just the same things, why would I even bother? Right? Well, the big difference between them is even though they can be parameterized equivalently, the learning of them are fundamentally different. So the way we do a Gaussian process, the benefit of writing down a Gaussian process is that we specify these incredibly strong priors over what we think the function class is. And then we have means now through our approximate inference to integrate out those beliefs, to basically really place structure on this space F, the hypothesis class that we said before. And if we have examples such as the wind farm example that I gave you before, or the transformation example that we had before, this might be something that I know a lot of. This implies that I can exploit that knowledge over that composition of the structure. And then I have, I'm sure, some parameters that I can maximize from that. In the neural network setting, we do not have that, right? So in this setting, I don't have a notion of it's not at all as easy to place that knowledge over that space of functions. The way I have to do it in this way is to often come up with some much unclearer way of defining an algorithm that will somehow find the solution that I want. Or what's even more common is that if you remember that plot with the red sine curve I had in the beginning, you have to increase the volume of data. By exploiting enormous amounts of data, you can then regularize the problem. So then, and I think I'm going to have to quit very soon, I'm not going to have time to go through this, then you can argue, well, shouldn't I do then the best of both worlds, right? Because the GP is going to be complicated and expensive to compute. Maybe I should do what people call a Bayesian network in this way. So I actually take this structure, which doesn't really provide me with uncertainties, it's a bit uninterpretable and so forth, but however, can't I just say, rather than taking this non-parametric GP approach to formulate the knowledge over the functions, I just become Bayesian over these parameters. And to me, this feels like really doing the worst of both worlds. Because what I've basically ended up with now is a model that's completely uninterpretable, because I specify prior over these things, but they tell me very little about it. It doesn't provide me an interpretation of the function at all. So I've regularized the problem, but I don't know in which way I've regularized the problem. And in addition, I get all the computational horribleness that's associated with doing Bayesian inference. So it just feels like you're adding a lot of computational complexity for basically no benefit whatsoever. That's just my view of looking at Bayesian neural networks. So I am going to, because I only have 5 minutes left, I'm going to be very, very quick. And sadly, we're going to have to miss this bit. Maybe I'll talk about this in the afternoon. I had some other things that I wanted to discuss, but at least I've highlighted a few things about composite GPs. So let's just summarize this. So we started off talking about unsupervised learning. If you read most machine learning books, it starts off with supervised learning is the way we normally do things. There's lots of models for it. Then unsupervised learning is apparently very hard. And then reinforcement learning is even harder. It's called the cherry on the cake, or whatever Jan LeCun says. My thinking is that unsupervised learning is not a thing at all. If it would be a thing, the way it's defined, it's not hard at all. It's really, really easy. Think about this, right? If you have kids and you ask them, go out and do a bit of unsupervised learning, right? That basically means go out and do whatever you want. That's really easy, right? You have no constraints to fulfill, right? The thing is, what makes it hard is that it is actually supervised learning, right? It's exactly the same thing. I'm not happy about any solution whatsoever. I want to do supervised learning, but I want to have a much vaguer input on the solutions that I want. And specifying these relevant assumptions that leads to the solutions that I'm interested in is really, really hard. So we need to input these very, very strong assumptions to get these sensible solutions out. And GPs is a really nice way of doing this. So, yeah, GPs provide these strong assumptions. So the next thing we talked about was composite functions. It's very important to know that composite functions cannot model more things. The image continuously shrinks. So what they can do is they can easily warp our input space to model less things. And this is really beneficial when you're building discriminative models. It's much less useful when you're building generative models. Often, this leads to very, very high requirements on data because they're very hard to restrict. So I like to show this thing because there feels to me, when we're looking at composite models, there seems to be this way of thinking, well, great, as long as we add some form of Bayesian inference to things, it's going to be better. But in order for any Bayesian model to make sense, at least to me, your prior needs to be interpretable. Because if you don't do this, you cannot interpret your solution. So I have this plot, and what I want to just show with this image is just saying, just adding uncertainties and distributions over parameters and integrating them out doesn't really buy you anything. At least that's my view of this thing. And with that, I'm going to be very quick and just end there with 2 minutes or 1 minute to spare.
Yeah, there's a bunch of questions that have appeared in the last couple of minutes.
I can imagine that.
Cool, yeah. Okay, so Hongbin, do you want to unmute if you want to ask your question directly?
Yes, thanks. So thanks, Carl, for this very nice talk. So my question is about the uncertainty quantification and the follow-up Bayesian optimization. So this is what interests us. So do you think it's possible to do such uncertainty evaluation using neural networks, or it's better to be done using the Bayesian neural network?
So I think the problem is this, right? So I think it's really hard to do uncertainty quantification using Bayesian neural network because I simply do not know what that uncertainty means. So I would much rather be of the view that you should take a non-Bayesian approach to that in this case, where you actually say, I'm going to directly parameterize the uncertainty and effectively learn another neural network to parameterize the uncertainty. Because I think the uncertainty that comes out of a Bayesian neural network to me just doesn't make sense, because I don't know what the prior is.
Okay, thanks.
Cool, thank you. Yeah, hope that answers your question. Simon, are you there? Do you want to ask your question? It's sort of like,
yes, I can.
Related. Yeah.
Hello, thanks for the talk first. I want to ask also about the Bayesian neural networks. There's a paper from Yarin Gal about dropout as an approximation for Bayesian neural network. What do you think about this method?
Can you say that again? I couldn't really hear.
There's a paper from Yarin Gal about dropout as an approximation for Bayesian networks.
Yeah, it's absolutely. So doing dropout in these things. So the question is what kind of uncertainty that is. You might be able to get some form of predictive uncertainty that basically says something about how effectively modeling what would be something of the noise in the data. But what you really want from an uncertainty, right, is to say, I make this assumption, this is what I believe, then I see some data, and this is what my updated belief about something will look given the evidence I saw in the data. And if I can't formulate, and at least this might be me being my limited way of understanding models that are parameterized by hundreds of parameters, is that I don't know what I started off saying. So therefore, I don't know what the output means either. And now what a lot of these papers try to justify is that, to me, is they say they can measure the output uncertainty. And then they say, look at this, this is the uncertainty I have in the data, and my model now models this uncertainty. But that's more just modeling noise. It says less about the knowledge relative to the prior assumption that you said.
Okay, thank you.
Cool, thanks very much. Yeah.
And also, I have to say, it's always a good point to try and say controversial things. So I say these things just to get people to have an opinion. So
excellent. There's one more question, but I think maybe it's more of a complicated question about a particular paper. So maybe that's best to leave till this afternoon as we're running over now. So is that okay? I think. Yeah, thanks again, Carl, for the talk. I think it's really a useful perspective on the stuff they've already sort of covered. Right, so this afternoon, let's just have a look at the program. So we've got a half an hour coffee break, and at 11 o'clock British summertime, Javier is talking about Bayesian optimization. Then we've got a lunch break. 2 o'clock is the lab sessions and the roundtables, where sort of I think there's quite a lot of questions probably people they want to ask you that they sort of realize they're out of time on. So yeah.
What I can say, I just want to say one final thing. The thing that I missed out on was explaining how horrible deep Gaussian processes are. I can include those slides as well.
That would be really interesting to hear.
Yeah. So I basically am annoyed by everything. So that's my
that's fair enough.
nature.
I mean, if there's a perfect method, we'd all have to.
There's none. None of these things work. Cool.
No free lunch. Yeah, and then emulation is in the evening at 4 o'clock with Neil. So that's great. Cool. So we'll see Carl again at 2 o'clock for the roundtable. Okay. Thanks everyone for taking part and the interesting questions. And thanks for the great talk, Carl. Yeah. Cool. I'll see you later.
See you later.